Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing an important class of organometallic compounds in the last few lectures, and this is about transition metal carbonyls. The transition metal carbonyl complexes are long known in the area of organometallic chemistry over a century and is sort of an old class of compounds which have been studied really lot as compared to the other class of compounds that we had discussed in the earlier lecture. For example, transition metal carbene or transition metal carbine complexes which only came to existence 30 or 40 years ago. So, transition metal carbonyl complexes have been studied a lot, particularly for their applications in homogeneous catalysis, as these transition metal carbonyl compounds are important intermediate in several catalytic reactions. For example, hydroformylation reaction, also these transition metal carbonyl compounds have been studied to get a quantitative estimation of electronic nature of other ligands, provides correlation of electronic nature of organometallic ligands, and this is done by infrared spectroscopy, and probably this is a very useful tool in gauging the electron donating ability of different co-ligands that appear with carbonyl compound in the organometallic complex, and that arises because of this MCO bond, where one measures the stretching frequency of these CO ligands. Now, if the metal is more electron rich, metal gives lower CO stretch, more electron rich gives lower CO stretch as a result of M to CO pi back donation, and that sort of helps one to get an idea of the nature of or electron density on the metal by looking at the CO stretch, and this is successfully employed in getting an insight on the extent of electron richness that a metal possesses by virtue of being bound to all other ligands around it. So, this has been used as an useful tool for getting a correlation of the electronic nature of various organometallic ligands that co-binds with carbon monoxide in organometallic complexes. Now, apart from this, in the last lecture we have also looked at binary carbonyls, and these are of the formula Mn COM. Now, what we have discussed in the previous lecture was that this for the binary carbonyls to occur, the transition metal has to be electron rich, such that Tm to CO pi back donation occurs that stabilize these transition metal carbonyl complexes that stabilize binary carbonyl complexes. Now, this also we had seen that this is an important hypothesis, and metals which are electron deficient metals, for example, early transition metals, electron deficient early transition metals like titanium, zirconium, hafnium do not form binary carbonyl complexes. So, this is an important observation, because binary carbon complexes are mainly stabilized by the ligand to metal as well as metal to carbonyl pi back donation, and the transition metals which are not efficient in displaying significant amount of transition metal to ligand pi back donation, for those complex transition metals the binary carbonyl complexes do not exist. And the example in this regard being titanium, zirconium and hafnium, which are group 4 elements and they are electron deficient enough to not facilitate the transition metal to ligand pi back donation. On the other hand, for electron rich late transition metals, where there is a significant amount of electron density at the metal, these elements do have a significant component of transition metal to carbonyl pi back donation. As a result, several binary complexes of these late transition metals starting from group 6 to group 9 are known. And with that brief background, we are going to take a look at various methods which are available for synthesizing these transition metal carbonyl complexes. Now, as transition metal carbonyl complexes require metal to ligand pi back donation for the stabilization of the carbonyl moiety, it is important that the metal be at low oxidation state for it to stabilize transition metal carbonyl complexes. And this being the theme of these methods which are available for preparation, we would see that the most of the methods conform to this idea of the metal being at low oxidation state, such that the metal is electron rich enough so as to partake in metal to ligand pi back donation. So, in that theme in mind, we are going to take a look at the first method of preparing binary metal carbonyls, and this is the simplest approach, whereby these binary metal carbonyls are prepared by direct reaction of metal with carbon monoxide. And these are sort of a very difficult compound to make. Some of them are volatile and also very toxic. For example, nickel plus 4 CO, 1 bar of pressure 25 degrees centigrade give this nickel tetracarbonyl. Similarly, direct reaction of iron plus CO at much higher pressure of 100 bar and higher temperature of 150 degrees centigrade gave this iron pentacarbonyl. And this shows that one can indeed make binary transition carbonyl complexes of late transition metal by direct reaction of the metal with the carbonyl gas. The high electron density of the metal because of its low oxidation state. Indeed, the oxidation state of the metal is 0 for both of the examples, and that facilitate metal to the ligand pi back donation. As a result, these binary alkyl carbene complexes are stabilized. Apart from the direct reaction of the metal with carbon monoxide, the other approach involved reducing a metal salt by a suitable reducing agent, and then treating that reduced metal salt with carbon monoxide to give transition metal binary carbonyl complexes. Some of the examples for this method are shown here. Metal salt plus reducing agent plus CO. So, the examples are six CO, C10, H8, 15, round 5, gives titanium CO6 2 minus plus K 15 round 5 whole 2 plus. So, here is a reaction where that metal salt is reduced by reducing agent, where the reducing agent is potassium, and then the carbonyl complexes of the same is obtained. Similarly, VCl3 plus 3Na plus 6CO in diglyne at 300 bar pressure gives sodium diglyne Me2 plus VCO6 minus, that in presence of H3PO4 eliminates hydrogen to give VCO6. So, here too we see that this vanadium trichloride in presence of a reducing agent with a sodium and carbonyl compound gives vanadium carbonyl compound, where the oxidation state of vanadium has reached 0. So, the other examples in this category is reaction of chromium trichloride with aluminum, CrCl3 plus Al plus 6CO gives 6H6 AlCl3 140 degree centigrade and 300 atmospheric pressure. Okay. So, that gives the chromium hexacarbonyl plus AlCl3. So, what we got is a flavor of this strategy, which involved the metal with a reducing agent and carbonyl. This is a very effective method with a lot more number of transition metal carbonyl complexes been prepared by using this method. Some of the representative examples of these are discussed here. Similarly, there are several miscellaneous methods available for preparing these transition metal carbonyl complexes, and these methods are for example 2 FeCO5 in presence of light and acetic acid produced Fe2CO9, and this reaction has been obtained as shown over here by photolysis reaction. The other involved also FeCO5 plus 2 OH minus giving HFeCO4 minus plus HCO3 minus. Then these 3 HFeCO4 minus plus 3 MnO2 gives Fe3CO12 plus 3 OH minus plus 3 MnO. Another reactions also involve this iron pentacarbonyl complex as FeCO5 plus XeF2 plus 2BF3 giving FeCO6 2 plus BF4 minus plus Xe. So, what is learned from here that there are other methods apart from going by the convention way of getting the carbonyl in the low valent oxidation state by a reducing agent or by the direct reaction of the metal, as opposed to that being the conventional. There are other methods whereby you can take a metal carbonyl and generate these transition metal other transition metal carbonyl complexes by this method discussed here. Now, with that we are going to go to some important aspects of these transition metal carbonyl complexes, particularly their structure. Now, structurally they form a diverse class of compounds where carbonyls are deposed around the metal center. They can occur as a bridging ligand as well as they can occur as a terminal ligands, and the bridging can expand the scope from 2 center to 3 center and so on and so forth. So, we are going to take a look of some of the important structures of transition metal carbonyl complexes. For example, nickel tetracarbonyl is a tetrahedral structure nickel is in 0 state. Iron pentacarbonyl is a TBP structure. Whereas chromium hexacarbonyl, so this is a tetrahedral structure, this is TBP structure, this is octahedral structure. So, we see that depending on the metal all sorts of possible structures are formed, and here is the structure of a manganese dimer that contains a metal-metal bond, So, each manganese is bonded to 5 carbonyl moieties, and then there is a metal metal interaction. Another example of a but all of these carbonyls are terminal in nature. Here is an example of a compound containing bridging carbonyl, which is dicobalt CO2 CO8. So, that means that there are 3 carbonyls on each cobalt. And there are 2 bridging carbonyls. So, what can be seen over here, that the carbonyl display diverse structures in this binary alkyl kind of compounds that can range from tetrahedral to trigonal bipyramid to octahedral, or dinuclear complexes that contains bridging carbonyl, as well as the ones which does not form one. And so, these diverse orientation is a hallmark of transition metal carbonyl complexes. We are going to take a look at 2 more such structures where similar diversity have been observed, and this is osmium carbonyl complexes, where you have 2 osmium also having 2 osmium and bridging carbonyl. Similar the structure of the iron compound. So, containing 3 bridging carbonyls. So, what we see over here, that Fe2CO9, and this is also OS2CO9, but what we see over here, that there are 3 bridging carbonyls as opposed to 1 bridging carbonyl as seen over here, and that is because that osmium being bigger in size, that the number of bridging terminal carbonyls are less, as opposed to iron, which is smaller in size, we see more bridging carbonyl atoms. So, let me just conclude what we have been discussing in this transition metal carbonyl complexes. We have looked at the synthetic strategies that are in place for preparing these complexes. Most of the strategy involved using either direct reaction of 0 valent metal with carbonyl, or metal salts getting reduced in presence of a reducing agent to its lower oxidation state, followed by direct reaction with carbonyl, and there are few other miscellaneous method that produces transition metal carbonyl complexes, including starting from some initial transition metal carbonyl complexes as reagents as well. After that, we have also looked into some of the structures of binary transition metal carbonyl complexes, and what came to the fore is that these transition metal complexes display a wide variety of structures that changes from the coordination number from 4 to 5 to 6 depending on the metal, and also they show various kinds of binding modes of the carbonyl ligand, which mostly are terminal as well as bridging, and depending on the size of the metal the number of the bridging carbonyl is sort of decided. So, with that I would like to conclude today's lecture on transition metal carbonyl complexes. We are going to take it up in more detail with more analysis being done on the geometry, structure, reactivity and property of these transition metal carbon complexes in the subsequent lecture that is going to come up next. With that, let me thank you for being with me, and also I look forward to take up this detailed topic in this next lecture. Till then, goodbye and thank you.